Thank you. So first of all, based on questions that were asked at the end yesterday, I want to clarify a couple of details. First, I was asked afterwards, why are we so interested in the Riesz-Leiter theorem? I should have made clearer at the beginning, it's the fundamental result about entanglement in quantum field theory, and since this school is about entanglement in quantum field theory and gravity, you can kind of think of it as one of the theorems that underlies the whole school. That's one point. Secondly, I was asked during the lecture if the Riesz-Leiter theorem means that operators in one algebra can be approximated by operators in the opposite algebra. I had intended but forgot to explain that the quantum mechanical example makes it clear that that's untrue. One set of operators, one algebra consists of operators of the form A times the identity. The other consists of operators of the form 1 tensored with B. All this is acting on the tensor product of two Hilbert spaces, where A maps HA to itself and B maps HB to itself. Now, I think it's obvious that these two operators can't be approximated by each other. The statement is that acting on the state we started with, they produce the same states, namely everything. So each can be used to produce all possible states from the same starting point, but the two operators are completely independent. Finally, during the lecture, it was clear that I was a little bit too hasty, or didn't explain fully enough the form I was taking for the state. So the general form of a state in the tensor product of the two Hilbert spaces would be like this, where you can assume that I sub A and J sub B are bases of the two Hilbert spaces. And then Cij are the matrix elements of a, in general, rectangular matrix, which I'll call C, where the number of rows is the dimension of HA, the number of columns is the dimension of HB. But then we consider Cij up to unitary transformations that act on the two Hilbert spaces. If we had a square matrix, we could diagonalize it this way. In general, here we have a rectangular matrix. Let's suppose, for example, that the dimension of HB is the larger one. Then the canonical form of Cij up to this kind of unitary conjugation on the left and right. If it's a rectangular matrix, there are leftover columns of zeros, and then there's a square piece which is diagonal, with the diagonal elements being positive, non-negative. So that's the form I actually assumed in the lecture. I just probably should have explained more carefully that I was putting a completely general state in this canonical form. So that's all I'll say about tidying up from yesterday, unless there is a question. If there isn't, we're going to go on today and to our second goal, and the goal is to explain why relative entropy is a good notion in quantum field theory. Maybe this time I'll make a point of saying at the beginning why we care about it. Two famous applications are Cassini's proof of the Bekenstein bound, which unfortunately probably no one is really explaining in detail at this school, and Wall's proof of the generalized second law. Maybe I'll have time to say a few words about these at the end of today, but I'm not sure. But anyway, there are very big applications in the subject of the present school, and that's why we're interested to know that relative entropy is a good notion in quantum field theory, though entropy is not. Entropy, as you essentially heard in the last lecture from Takenagi, and also as you heard from Bueno, is divergent in quantum field theory. But relative entropy is not and so our goal is going to be to understand how to properly define relative entropy in quantum field theory. But along the way, we're going to learn a bunch of other things. So for instance, let's take this situation where we have an open set U and a space-like separated open set V. Then we have the two algebras AU and AV. We'll find that given a cyclic separating state. Now, we proved yesterday that the vacuum in Minkowski space is cyclic separating. But cyclic separating, remember, means that the Riesz-Leiter theorem is true for both U and for V. So acting on psi, all operators in U or operators in V create states that span the whole Hilbert space. So given psi, we'll find a natural operator that exchanges the two states, the two algebras, sorry. So that's part of what we'll do. And you'll come as close as you can. Another way to say what we'll do is that we'll come as close as one can to defining density matrices. In quantum field theory. Density matrices of a region can't be defined as Bueno described. There's a partial substitute, and we're going to sort of prove the existence of that partial substitute. So there is going to be an operator given a state that will exchange the two algebras, but there's a trick about the property of this operator, and I'm going to explain in two ways what that trick is. First, I'll illustrate it with a special case. The special case will be the case that the state is the vacuum, and U and V are opposite Rindler spaces. So the setup is like this. In some Lorentz frame where T goes vertically and space goes horizontally, the spatial coordinates are x and also some perpendicular coordinates, which I'll ignore. You can think of it as being two-dimensional. U is defined by x being bigger than the absolute value of the time, and V is defined by x being less than minus the absolute value of the time. So V is here and U is here. And in this example, first of all, in this example, I claim there's a well-known operator that exchanges U and V. But what is this operator? Your first thought might be that it's parity symmetry. But there's something wrong with that because the general quantum field theory is not parity invariant. What's a universal symmetry that exchanges, that reverses the direction of space, the orientation of space? The only universal symmetry, first of all, there is a universal symmetry that exchanges U and V, but it's not just parity. The only universal symmetry is what I'll call CRT. Charge conjugation times a spatial reflection times time reversal. You're probably accustomed to thinking of CPT. P, parity in 3 space dimensions, is the same as a reflection of one coordinate and a rotation of the other two by pi. But it's really, if you want to work in an arbitrary space-time dimension, it's more natural to think of a reflection of one coordinate rather than insisting on trying to rotate them all. So the universal symmetry is CRT, and it does exchange the two Rindler wedges. So in quantum field theory, there is a universal symmetry that maps the vacuum to itself and exchanges U and V, and therefore exchanges the algebras AU and AV. But it's anti-linear. It's not linear. Well, it's anti-linear and in fact anti-unitary. So I wanted to make 2 points by giving this example. First, to show that the natural symmetry that exchanges the two algebras exists. But secondly, I wanted to prepare you for the fact that it's anti-linear, not linear. So to find a way of exchanging the two algebras, as this example shows, we will have to be prepared to look at anti-linear symmetries. But we can also see that from the general quantum mechanical setup. So our state, in general, up to a change of basis, our state was like so. And now, if I ask you, well, first of all, remember the state was what chose the bases. So we're not going to find a natural map between two Hilbert spaces A and B if we know nothing about them. But here, the state correlated basis vectors in A with basis vectors in B. So you might think, well, that obviously gives us the information we need to exchange the two spaces, and you might propose that I should define this symmetry. But a little thought will show you that there's a problem with that, because although we pick the C's to be positive, we have nothing that determines the phase of the state IA. And we could replace IA by e to the I times an arbitrary phase, phi I, times IA. We would do the same thing, or actually we have to do the opposite with an opposite phase for I sub B. That would leave psi invariant. So a choice of psi does not completely determine the states IA. It determines them up to phases, with opposite phases for the other guys. And you see, if we make this change of phase, an operator that exchanges I sub A with I sub B is changed. So it's not true that there's a natural operator that exchanges IA with IB if you think it's linear. So an exchange of IA with IB, well, let me say this better. An operator that maps IA to IB is not well defined, meaning it's not invariant under these phase changes if you think it's linear. But it's okay if we consider it to be anti-linear. Because if it's anti-linear, that exactly tells us that if we rotate IA by a phase, we have to rotate IB by the opposite phase, which is exactly the situation that we're in. So it is a true fact of quantum mechanics that given a cyclic separating state, in other words, given a state that has the Riech-Leiter and dual Riech-Leiter properties for both algebras, we have exactly the information we need to define an anti-linear map, and in fact anti-unitary, between the two systems. We do not have the information we would need to define a linear map. We have the same problem we had in the back here. Here, the CRT theorem says that we would have reflection symmetry if and only if we have time reversal symmetry. So precisely if there's time reversal symmetry, we could have then used CR instead of CRT, and it would then be a linear symmetry. So here, if we had time reversal symmetry, we could ask that the states IA with the time reversal invariants, and that would fix their phases up to sign. And if we change the sign of IA, we would change the sign of IB by the same amount. So then, in the time reversal invariant case, we would have a linear map between the two systems. But that linear map would simply be time reversal times the natural antilinear map. The fundamental fact is that with no assumption, there's an antilinear symmetry here and also here, because the map from IA to IB makes perfect sense without any more information except the choice of the state psi as an anti-unitary map from HA to HB. So in this case where we're given a fully entangled state between two systems, or where we're given space-like separated regions like this in quantum field theory, or like this, what we're going to look for is a natural anti-unitary map that exchanges the two systems or the two algebras. So any questions? Oh, I'm glad that was also clear that there weren't any questions. Okay. So now we go back to this general situation where there's no obvious symmetry between the two regions, but nevertheless, we'll find an anti-unitary map from one algebra to the other. What we'll do is we'll first find an anti-linear map, and then we'll make it anti-unitary. So first, just a simple anti-linear map. It won't be anti-unitary. Then we'll improve it to make it anti-unitary. The anti-linear operator is going to be the Tomita operator, it's called. It depends on the choice of the state psi that obeys the Schlieder theorem and the algebra AU. So I could give it a lot of indices, like S psi U. But I'll just abbreviate all that and just call it S. So it's defined as follows. If A is in the algebra of region U, then I define S by saying that S of A on the state psi is going to be A dagger on psi. That's anti-linear because if you multiply A by a complex number, A dagger would be multiplied by the complex conjugate number. So this mapping is anti-linear, not linear. But we have to explain why it's well defined as an operator. First, the Riesz-Leiter property says that the states A psi span the whole Hilbert space. So this does define the operator S on a dense set of states. Well, secondly, we need to know there's no inconsistency. There'd be an inconsistency if we had A psi equals 0, but A dagger psi not equals 0. Because then we'd be trying to say that S on 0 would be something non-zero. But the dual Riesz-Leiter theorem says that never happens. The dual Riesz-Leiter theorem says that if A psi is 0, then A is 0, and therefore A dagger is 0, so A dagger psi is 0. So the Riesz-Leiter and dual Riesz-Leiter theorems exactly say that S is well defined. S is anti-linear, but it's not anti-unitary. So what we're going to do is to take the anti-unitary part of S. So when you studied linear algebra, you might have learned about what's called the polar decomposition of an operator. It's usually stated for linear operators. The polar decomposition, well, it's analogous to the fact that any complex number, lambda, is a positive number, p, times a phase. This is positive. This is a phase. That's the polar decomposition of a 1 by 1 matrix. The polar decomposition of an operator O that takes a Hilbert space to itself is that O is a positive operator times a unitary operator. That's true, but I'm going to write the unitary operator first. It can also be written as a unitary operator times a positive operator. In the 1 by 1 case, we didn't have to worry about the ordering. So that's the polar decomposition of a general operator on a Hilbert space. And you may have learned about it when you learned linear algebra. If you didn't, then as a shortcut, you could count parameters and see that U and P seem to have enough degrees of freedom so that we should be able to write an arbitrary O in terms of this. So this decomposition exists and is unique. Well, for the 1 by 1 case, you know that every complex number is uniquely a positive number times a phase. So this generalizes that to n by n matrices and more generally to Hilbert space operators, perhaps in infinite dimension. You're more likely to have learned the polar decomposition for linear operators, while here we have an antilinear operator. But for antilinear operators, the same thing is true. If O is antilinear, the same is true except that either U or P will be antilinear, but not both. I believe the statement is true either way, but for us, U will be antilinear. I keep spelling linear wrong, but U will be antilinear and P will be linear. So we'll use the fact that in our application, what will be this Tomita operator S. We use the fact that the Tomita operator, like any operator, is like any antilinear operator. It's an anti-unitary. So it's an anti-unitary operator times a positive operator. But in the case of the Tomita operator, though, which I remind you the definition, and now I realize I forgot to say that S squared was 1. So you see, S squared of A psi is S of A psi. But S of A psi is A dagger psi. And S of A dagger psi would be A dagger dagger of psi, which is A psi, which showed that S squared is 1. So one fact about S is that S squared is 1, but then we have the polar decomposition. It's usually written as J times delta to the 1/2. J is anti-unitary, and delta to the 1/2 is positive. So we've discovered an anti-unitary operator, which will turn out to be the operator that exchanges the two algebras. And it's dependent on the choice of this cyclic separating state psi, that is, the state that obeyed Riechlider and dual Riechlider. Now, since S squared is 1, we have J delta to the 1/2, J delta to the 1/2 equals 1. And we can write that by saying that J squared times J inverse delta to the 1/2 J is equal to 1 times delta to the minus 1/2. Now we're going to use the fact that the polar decomposition is unique. So what's written here is two different polar decompositions of the operator delta to the minus 1/2. It's already positive, so it's the anti-unitary operator 1 times itself. But it's also J squared times what you'd get by conjugating it by J inverse. Since delta to the 1/2 is positive, its conjugate is also positive. And this is anti-unitary, because it's the square of an anti-unitary operator. So we have two different polar decompositions of the same operator. And since the polar decomposition is unique, we learned that J squared is 1. And we also learned that J inverse delta to the 1/2 J is delta to the minus 1/2. Which I think I won't use, but you can check it with things we'll prove later. So we've discovered, or we found an anti-unitary operator in this general setup, but we want to understand what properties it has. And so we're going to discover that by checking what its properties would be in a general quantum mechanical system which was the product of two subsystems, A and B. And then, since quantum field theory is a limit of that, any statement that holds in a limit will be true, but some statements will be lost in the limit. I'll explain how that comes about. I'll stop here for questions, though. No? So we're going to see what this means for a standard quantum mechanical system, where the state is the sum of Ci times Ia tensor Ib. This could be in either finite or infinite dimensions. And the sum, what I'm writing as a discrete sum could be a continuous integral. So this could be a cutoff, a lattice approximation to quantum field theory when I write the states this way. And we'll learn something about it, and then we'll discuss what remains true in the continuum limit. So A is supposed to be in the algebra that acts on the system A, and B, I think yesterday I just called curly A the algebra that acts on HA to itself. And let's say B will, well, if I need it, will be in the algebra B that maps on system B. So an example of an operator A would be the operator that takes IA to JA and annihilates JA if J is not equal to I. So that's an example of the operator A. That's an example of an operator in the A algebra. It's just an example of an operator on system A. And the definition of S tells us that S of IA S of A psi is A dagger psi. Writing that out in more detail, S of A on the sum of Ci times IA IB is A dagger on the sum of IA IB. But A maps I to J and annihilates everything else. So the left-hand side is S on Ci times JA IB. So A dagger maps J to A and kills the others. So given that, well, the left-hand side is what I've written here, but the right-hand side, I has to equal J. See, for A dagger on IA to be non-zero, I has to equal J. And then it will map the state to I. So this condition for this operator, for different choices of I and J, tells us this, except I'm slightly worried I made a mistake in trying to write it. Sorry. I think it comes out like this. So remembering that the C's are all positive, well, actually, they're strictly positive because we assume the dual Riechlider theorem. We assume Riechlider and dual Riechlider, so the C's are all strictly positive. So what we learn is that what we learn from this is that S of the state J of system A times I of system B is Cj over Ci times I of system A times J of system B. So this is not anti-unitary unless the C's are all equal. But it's easy to take its polar decomposition. Well, the polar decomposition where S is J times delta to the 1/2. J is just the operator that takes JAIB to IAJB. And delta is the operator that takes IAJB to itself times something. The something is Cj squared over Ci squared. S hat is Cj over Ci, but since we wanted delta to the 1/2 here, we have to delta roughly has for its eigenvalues the eigenvalues of S, which are these things. So, but this is delta to the 1/2, so delta has squares. So, you see, J is the naive. Operator that exchanges systems A and B, mapping IA to IB. That's what this formula tells us. So, the naive operator we knew about, we've learned it can be. We didn't need this discussion to see that once we have this kind of state, we can define an antilinear operator that exchanges IA with IB. But we needed, in that reasoning, we needed this state written in a tensor product Hilbert space, HA tensored HB. That tensor product decomposition isn't correct in quantum field theory. We wanted a definition that was more robust so it made sense in quantum field theory. That's what we had here, because here the definition of S only used things that make sense in quantum field theory, and the polar decomposition is a true fact about operators, so that also was true. So we were able to define J in quantum field theory, but J has the property that in an ordinary quantum system, it would reduce to the obvious exchange of the two subsystems that we can define once we have a cyclic separating state. So we've generalized in a way that makes sense in quantum field theory what would have been the obvious definition in quantum mechanics. Now we can also see something interesting about delta. Delta can be written, see delta, since it maps IA to IA with some eigenvalue and maps JB to JB with some eigenvalue, it's the tensor product of an operator on system A times an operator on system B. And a little thought will show you that delta is the inverse of the density matrix of system A tensored with the density matrix of system B. Because with our state, the density matrix of system B is the sum of Ci squared times the operator that projects onto I of system B, and the density matrix of system A is the same thing for A. And since delta was diagonal on that basis, with eigenvalues Cj squared on B and 1 over Ci squared on A, delta when there are density matrices, can be written in terms of density matrices. What we learned from this for quantum field theory, though, is that in quantum field theory we can't define density matrices, but this particular combination of the density matrix of one system and the inverse of the density matrix of another system, we were able to define in a way that was robust enough that it did make sense in quantum field theory. So we've learned, roughly speaking, how much of the usual formalism of density matrices does make sense in quantum field theory. Now, so let me pause here again for questions. None? I'm slightly worried this time it means I lost you instead of everything having been clear.
I can ask something.
Okay, good.
So the reason why J is not the one we need for a quantum field theory is because we checked that in a quantum field theory it could not be the naive one.
No, we didn't. Well, in quantum field theory, we found that we would have CRT is antilinear, so that told us in general we have to look for antilinear symmetries. And we found an antilinear symmetry because S was antilinear, so J was antilinear. So we found in general, we haven't quite drawn the lessons for quantum field theory yet. We have to go back to it. But when we draw the lessons, we will have found a general antilinear operation in quantum field theory that exchanges the two algebras.
But this won't suffice, and we don't know yet why.
Don't know what?
Yet why this won't suffice for.
Well, I haven't yet taken the limit of these statements. I defined delta and J in a sufficient generality that it made sense in quantum field theory. But we didn't prove what properties they had yet. Then, for a quantum system where you do have a tensor product definition of the decomposition of the Hilbert space, we did prove what properties J and delta would have. Then I'm going to state those properties in a way that will remain true in the continuum limit. So some things will not be, an example of what's not true in the continuum limit is that there's a tensor product decomposition of the Hilbert space. But we will see some things that are true in the continuum limit. So for example, so for an ordinary quantum system, by ordinary I mean that there is a tensor product decomposition of the Hilbert space. J exchanges HA and HB. Now, we will not be able to say that in quantum field theory, but instead we'll draw a lesson from it that we can say. So it follows, again for the ordinary system, that J of algebra A times, remember, J squared is 1, so it doesn't matter if I write J or J inverse. J or J inverse, conjugating algebra A by J will give us algebra B and vice versa. J exchanges the two Hilbert spaces, so it exchanges the two algebras. In quantum field theory, we can't say that J exchanges the two Hilbert spaces since they're not defined, but we can say it exchanges the two algebras. I keep learning new things this pen can do. See, imagine taking a cutoff, a lattice approximation to a quantum field theory. With the lattice in place, the Hilbert space is a tensor product. Then we define the operator J, it's anti-unitary. We take a limit. A limit of anti-unitary operators is still anti-unitary. So, in the limit, J will be anti-unitary. And a statement like this is true in any limit. So, the decomposition of the Hilbert space does not survive in the limit, but the fact that J exchanges the two algebras does survive. And in the case of Rindler space, with psi being the vacuum. J is equal to CRT. Okay, so that was, okay, so that's what we say about J in quantum field theory. It's an anti-unitary operator that exchanges the two algebras. Now let's discuss what we can say about delta in quantum field theory. Well, it's an unbounded operator. Well, it's positive. Okay, it's a positive operator that's unbounded, densely defined, but those properties don't go away in a limit. So, well, anyway, we directly defined delta in a way that made sense in quantum field theory. We defined the Tomita operator, that was well defined, and then its polar decomposition gave us the definition of delta. So we know delta exists in the quantum field theory as a positive operator. But this factorization doesn't make sense because the Hilbert space factorization doesn't make sense. But there's something that we can learn from that factorization that is true in the limit. So I'm going to tell you a consequence of this factorization, which in the ordinary quantum system is a simple consequence of this factorization. But its nature of the statement is that it will be true automatically in the limit, the continuum limit. So going back to ordinary quantum mechanics, we have delta equals rho A inverse tensor rho B. So delta is the product of an operator in A times something that commutes with A. Namely, rho B commutes with A and rho A is in A. So we're going to exploit that. But in exploiting that, it's better to work with unitary operators, so we're going to work with the operator delta to the IT.
Sorry,
Yes?
could you repeat the last part that you mentioned, the product of A and that stuff?
Well, rho A acts on the system A, so it's in the algebra curly A.
Yeah.
Rho B acts on the algebra B, so it's in curly B.
Okay.
And that means rho B commutes with the algebra curly A. So delta is the product of an element of A and something that commutes with A. Now I'm going to work with the unitary operator delta to the IT, which you can also call delta equals e to the minus ITH, where h is minus log delta, sometimes called the modular Hamiltonian. But it's important that here we're talking about the two-sided modular Hamiltonian, sometimes called the complete modular Hamiltonian by some authors. The one that's well defined. So it's a unitary operator. And now I'm going to make the following statement, first of all, for the ordinary system. Delta to the IT, first of all, since delta to the IT is unitary, well, conjugation by delta to the IT maps the algebra A to itself. Why? Because delta to the IT is the product of an element of A, namely rho A to the minus I to the IT. Oh, sorry. Delta to the IT is also the product of an element of algebra curly A times something that commutes with it. This commutes. So when I conjugate the algebra A by delta to the IT, nothing happens. When I conjugate with delta, rho B does nothing, but rho A is in the algebra A. So rho A to the minus IT is just a unitary element of the algebra A, so it conjugates A to itself. So we have these statements. I've written something that's completely trivial, but I'm worried I've done it in a way that was confusing. Delta is a unitary operator. Delta to the IT is a unitary operator, but it's the product of an element of A, which trivially conjugates A to itself because A is an algebra, and an element of B, which commutes with A, so it doesn't do anything to A. So that's the reason for this statement. And the reason for this statement is that delta to the IT is the product of an element of B, which trivially conjugates B to itself, times something that commutes with B, namely rho A to the minus IT. And since it commutes with B, it does nothing. So we have these statements. Now these statements automatically are true in any limit. They're automatically true in the continuum limit.
Why is that the case?
Well, an element of the algebra in the limit was the limit of algebra elements, and each in the lattice cutoff system, and delta to the IT conjugated the cutoff lattice element to an element of the cutoff algebra, and then you take the limit. If you think about it for a little bit, this kind of statement is automatically true in a limit. Let me give you an example of a statement that's not automatically true in a limit, in fact isn't true in a limit. Okay? So here we had delta equals rho A inverse tensor rho B for a cutoff system. This kind of statement doesn't necessarily survive a limit because we don't know that the operators rho A and rho B have limits. The problem with this kind of statement is roughly that rho A and rho B both fluctuate too much so that they don't have limits, but their fluctuations cancel so that delta does have a limit. We know delta has a limit because we defined it at the beginning. We defined the Tomita operator at the beginning, and delta was it came from its polar decomposition. So delta is guaranteed to have a limit, but rho A and rho B are not guaranteed to have limits, and in fact do not have limits. And this factorization doesn't guarantee a limit, basically because the two factors, well, a simple thing that could happen is that rho A and rho B could have fluctuating diagonal terms, C-number terms that cancel. But anyway, this kind of statement doesn't necessarily have a limit because rho A and rho B themselves don't have limits. But this kind of statement automatically has a limit. Yes?
It's not dependent on how I define delta IT.
There's no ambiguity about defining delta to the IT. When you studied, well, you probably learned about it when you learned quantum mechanics. One way to say it is you diagonalize delta. Delta to the IT has the same eigenvalue as delta, but each one is raised to the IT power. Since delta is positive, that's unambiguous. You should, if you weren't sure how to define delta to the IT, you should have asked the first time I wrote it down. But from our general study of quantum mechanics, we should know that if delta is a positive operator, delta to the IT is well defined. It's the same thing, you see, its eigenvalues are positive numbers. A positive number to the IT power is well defined as a statement about complex numbers. And we just do that for each eigenvalue. That's one way to say it. Any other questions? Yes?
The argument to why J also flows nicely in the limit is similar to why delta.
Well, we defined, before we did anything, we defined J. Right? So we knew, we didn't at the beginning know what's the physical interpretation of J, but we knew that, at the beginning we didn't know that J exchanged the two algebras. but we did know that J was well defined. In any cutoff version, J exchanges the two algebras. We then proved that. So in a limit, it also exchanges the two algebras. J does depend on the state. Yes. And that was obvious in the general quantum mechanical system. In quantum mechanics, to get started, we picked a state. Well, J for this kind of system just exchanges the basis IA of system A with the basis IB of system B. But those bases are determined in terms of the state. There's no way for two abstract quantum systems A and B to know how to exchange them without more information. And the more information is provided by the cyclic separating state psi. Any other questions?
Does this delta allow you to prepare new and cyclic and separating states for the algebra?
I'd say it more tells you how to study cyclic separating states rather than preparing new ones. So I think I've got 21 minutes. Okay, so first I want to explain concretely what all this means for Rindler space. Unfortunately, I'm not going to have time to prove the statements. One of the places you could see proofs is actually in my lecture notes that I cited yesterday, the ones that have the word entanglement in the title. But for in defining Rindler space, we picked a time coordinate and one space coordinate. There were more space coordinates we didn't talk about. So then there's a Lorentz boost that we can define. It's the Lorentz boost of the xt plane. Right? I have a time coordinate and a space coordinate. I've picked them in defining Rindler space. Then there's a boost operator in that plane, which can be defined by this formula. So delta is actually e to the minus 2 pi k. So delta isn't unitary, but delta to the it is e to the minus 2 pi it times k. And that's an ordinary Lorentz boost of the xt plane. And as you know, or as you hopefully know, the Lorentz boost of the plane maps the Rindler space to itself, so it maps the algebra of the Rindler space to itself. So the statement that delta to the it conjugates the algebra of region U to itself, in this case, is the statement that the algebra of Rindler space is Lorentz invariant. It's mapped conjugated to itself by Lorentz transformations. And similarly, the algebra of the opposite Rindler space is Lorentz invariant. And in this example of Rindler space, J is equal to CRT. Sorry. For Rindler space, I assume that the cyclic separating state considered is the vacuum. Then, given that, it's true that delta is e to the minus 2 pi k and J is CRT. Now, I'd also like to explain in this example why we can't factorize delta as a density matrix times another density matrix. To try to factorize it, we define k right as the part of the integral defining k where x is non-negative. And we define k left as the part of the integral where x is non-positive. I'm going to put an absolute value on x there because x is negative in the region that enters in k left. So k is k right minus k left. And therefore delta, well, okay. To try to factorize delta, we'd write delta as e to the minus 2 pi k left times e to the plus 2 pi k right. Sorry, plus and minus. That's what the factorization would try to be. The only trouble with that is that k right and k left don't make sense as Hilbert space operators. K left and k right acting on the vacuum, for example, has infinite norm. Its norm would be the vacuum excitation value of k right squared. Likewise for k left on the vacuum. And replacing the vacuum by some other state doesn't help. K right on any Hilbert space state the reason is that when you try to calculate, well, first of all, the norm of the state with the k right dagger, k right in the state, but k right is self-adjoint formally, so that would be k right squared in the state. So k right is an integral, so this would be a double integral. I'm going to write quickly, I'm going to ignore the, well, I should include the y coordinates, but I'm ignoring them as if we're in 1 plus 1 dimensions. So the norm is given by the 2-point function, a certain integrated 2-point function of the stress tensor in the state. And the integral diverges near the endpoint, near x equals 0. We'll discuss such things a little bit more systematically next time. I don't want to say more about it right now, I don't think. But it's a true fact that k right is not a well-defined operator because acting on a Hilbert space state, it takes you out of Hilbert space. Likewise, k left. Well, the problem cancels in k. K is simply the Lorentz boost operator, and as you all know, the Lorentz boost operator is in fact well-defined. So remember, at the very beginning, we defined delta in a way that was guaranteed to make sense in the continuum limit. But nobody guaranteed us it would have a factorization in the continuum limit, and it does not. The things that we proved were true. We defined J as an anti-unitary operator, delta as a positive operator, and then we proved certain things had to be true because they were true for the cutoff system, and they're automatically true in limits. But the factorization is not such a property. Any questions? Yes?
Is that infinite energy that you need to stay in the Rindler wedge as a massive observer?
Well, the details of the Rindler wedge aren't important here. If we had integrated the energy density over any finite region D in space, we'd have the same problem near the edge. Sorry, here there were a couple of factors of x and x prime that I forgot. But anyway, they don't matter either. We'll discuss at the beginning next time what kind of smearing of quantum fields actually gives operators. And it's delicate. And a typical example that doesn't give an operator is KR. And we'll likewise see next time, an important example we'll see next time is that anything on the black hole horizon doesn't give an operator. Any other questions? Yes?
You talk about the Hilbert space, and then you talk about the operators who are defined.
Yes?
And then there are some operators that are not well defined. So what are well defined and not well defined?
Well, I think the question really should be, what is KR if it's not an operator? It has matrix elements. So, psi 1 KR, psi 2. We study things that aren't operators all the time. That's why this is confusing. So it can be finite for suitable psi 1 and psi 2. For example, it's 0 if psi 1 and psi 2 are the vacuum. So it can have matrix elements. The way mathematicians would say it is that it makes sense as a quadratic form. It doesn't make sense as an operator. An operator is something that has eigenvalues that you can measure. If it had an eigenvalue, that would be a state with the property that kr squared would be finite in that state. In fact, it would equal lambda squared times the norm of the state. Right? But kr squared has the property that its expectation value in any state is infinite. So kr takes you out of Hilbert space. We'll say more at the beginning next time. So certain smearing of local fields make operators, but kr doesn't fill the bill, so it's not an operator. It makes sense as a quadratic form that has matrix elements, but it's not an operator that can map Hilbert space to Hilbert space. So the density operator, the density matrix, we don't just use the matrix elements of the density matrix. The density matrix is actually an operator. So here we actually were looking at a nonlinear function of kr, so we wanted kr squared and even nonlinear functions of kr to make sense. So kr has matrix elements, but nonlinear functions of kr don't make sense. The reason you might be confused is that in physics, we very often deal informally with things that we call local operators that aren't really operators. They have matrix elements, but they're not operators. We'll say more at the beginning next time. Yes?
Can this be related to the Rieger-Hilbert space formalism?
To the what?
Rieger-Hilbert space.
I can't hear the first word. What Hilbert space? What? Not very closely, I don't believe. I'm not sure. I might be missing something. Yes?
I don't see how the delta by T is a Lorentz boost.
It's a true fact that it's a Lorentz boost. K is the generator of Lorentz boosts. Lorentz boosts are unitary operators. I define K to be self-adjoints. So the exponential of a self-adjoint operator isn't unitary. To get a Lorentz boost, which is a unitary operator, you have to raise K to an imaginary power. That's what you learned when you learned quantum field theory, I can assure you. Any other questions? Yes?
When you have the Hilbert space and then you talk about the algebra, once you are giving a Hilbert space is a well-defined set of operators you have on the Hilbert space.
Yes.
For which you can. So this is precise.
It's precise, but I didn't make it completely precise because filling in too many, crossing and filling in all the gaps and dotting the i's and crossing the t would have taken too long. So I was a little informal in my explanation. But the algebra consists of well-defined operators made from the local fields. I will tomorrow explain it. At the cost of making too many promises. I'm hoping to not have promised too much. Any other questions, quickly? Okay, sorry. Now, unfortunately, okay, so I have told you roughly as much of density matrices as makes sense in quantum field theory, but it wasn't quite enough to tell you how to define relative entropy. For that, we need a generalization. The generalization is called the relative Tomita operator. Well, it's the relative everything. The relative Tomita operator. Well, I didn't actually tell you. Delta is usually called the modular operator. And J is the modular conjugation. So now we're going to define the relative modular operator and relative conjugation. except I'm not going to go into as much detail, partly because we don't have the time. So, we're going to do something more general that makes sense in complete generality. So, psi will be a cyclic separating state. For example, the vacuum. And phi will be any state. And now we define the relative Tomita operator. We'll talk, unfortunately, it's hard to avoid mentioning the state, so I'll call it S of psi phi, by saying that acting on, well, I'll define it in a way that makes sense generally. So, A is in the algebra of region U. Acting on A psi, it's equal to A dagger of phi. It's well defined for the same reason it was well defined when phi equals psi. Because the state psi is separating, states A psi are dense in Hilbert space, so this does define the operator we're trying to define on a dense set of states. And there's no contradiction because whenever the left-hand side is 0, the right-hand side is 0. Whenever A psi is 0, A is 0, and therefore A dagger phi is 0. So this is the relative. So this is well defined even in quantum field theory. And then we make the polar decomposition again. And now I can define relative entropy. This will be Araki's definition of relative entropy. In a sense, in a way that makes sense in complete generality for operator algebras, in particular for quantum field theory. The relative entropy between two states psi and phi for the region U is equal to the expectation value in the state psi of minus the log of the relative modular operator. So, well, we need to know that it makes, so delta is still positive, of course. And the logarithm of an operator makes sense for operators. The logarithm of a positive operator makes sense. The logarithm of a positive number is well defined. It might be negative, but it's a well-defined real number. And if you like, diagonalizing delta and then taking the logarithm of each matrix element gives what we mean by the logarithm of delta. And then we simply take minus the expectation value of log delta in the state psi. That's Araki's definition of relative entropy. And clearly, the way we've defined it, it makes sense in quantum field theory. The only thing that might not be obvious is what it has to do with an elementary definition of relative entropy in quantum mechanics. So, to compare to what you may know better, to what may be the usual definition, we would look at an ordinary quantum system with a decomposition, and then phi is some other state which has a similar decomposition in a different basis, right? Oh, sorry. Of the two states, psi and phi are not simple in the same basis. Each one is simple in its own basis. So psi has this decomposition in the basis of states IA and IB. There's some other basis, alpha A and alpha B, in which phi has the same kind of decomposition. And then, I won't do it for you because we're running out of time too much, but similarly to what I did when phi equals psi, you can calculate explicitly from these formulas what are S psi phi, J psi phi, and delta psi phi. You can also find the computations in my lecture notes if you're interested. And for today, what we need is that what you learn for delta psi phi is that it's, well, it's again written in terms of density matrices. Well, I'm slightly worried I've got the inverse in the wrong place in my notes. It's something like sigma A tensor rho B inverse, where sigma A is the density matrix of phi for the algebra A, or the system A, and rho B is the density matrix of psi for the other algebra. So anyway, you have to calculate similarly to what we did before from the definition of S and from this form of the states. You work out explicitly what S is and therefore what J and delta are, similar to what we already did. And you get this formula for J, for delta, I mean, sorry. And then you find that the expectation value in psi, let's go a little bit more slowly. So you learn, therefore, that log of delta psi phi is log sigma A tensor 1 minus 1 tensor log rho B. So the expectation value in the state psi of minus log of delta psi phi These are things you can work out using the definition of a density matrix. Here we have the matrix element in the state of an operator on system A times the identity on system B. So by definition, that's equal to the trace of the operator log sigma A in the density matrix of the state psi for system A. This will be the trace in system A. And similarly, this one, well, here we have the identity in system A times an operator in system B. So by definition, that's the trace for system B of rho B times the operator, which here is log rho B. But since rho A and rho B have the same eigenvalues, this is the same as the trace in A of rho A log rho A. So what we got, except I think I've made a sign mistake someplace, is minus the trace of rho A log rho A minus rho A, minus rho A log sigma A. And that's the usual, somewhere we got a minus sign. I'm afraid I zipped through some of this too quickly for my own good. But apart from the minus sign, this is the standard definition of relative entropy in quantum mechanics. So what we accomplished was we defined something that we could define in generality, also for quantum field theory. And then, except that I skipped the generalization of the computation we did before to the case that phi is a general state not equal to psi. But in quantum mechanics, by imitating the previous calculation, we discover this formula. And based on that formula, we compute the matrix element and we recover the usual definition.
I think that line is the minus sign missing.
Where?
You have the minus in front of the dot.
Oh, maybe it was just here. Okay. Maybe. Okay. Okay, hope so. Well, hopefully there weren't more mistakes. I'm pretty confident it's written carefully in the lecture notes, though. Any other questions very quickly? So we defined relative entropy for quantum field theory, and I told you it's got at least two really important applications, for which I have minus 3 minutes. Okay. Well, I'm going to take 2 minutes to say something about one of them, and I'll have to skip the other. So Cassini proved the Bekenstein bound, and what he needed to know was that relative entropy for a region U is non-negative in quantum field theory. So I'm just going to prove it based on the definition we used. Well, the fact I'm going to use is that the logarithm of an operator. Well, a fact about numbers is that log x is less than x minus 1. So therefore, it's also true for operators. Because it's true for each eigenvalue. So minus log delta, therefore, is greater than 1 minus delta. So the expectation value in the state psi of minus log delta is equal to or greater, we assume the state psi is normalized to 1. It's equal to or greater than the expectation value in psi of 1 minus delta. And the 1 term gives the norm of the state. The other term is, minus the expectation value of delta in the state psi. That's, as I'll explain to you, that's also equal to 1. So the difference is 0. So this proves, in a generality that makes sense for quantum field theory, that relative entropy is non-negative. You see, since S was J delta, it follows, though I didn't say so, that S dagger S, delta is S dagger S. I didn't say that before, but it follows from this relation immediately. So the expectation value of delta in the state psi is the expectation value of S dagger S. But S being antilinear, we can move it over, replace S dagger with S and complex conjugate. But S psi is S of 1 acting on psi, which is 1 dagger acting on psi, which is psi. So that showed that the extra term in this relation was 1. So the argument proved, therefore, that relative entropy was non-negative in quantum field theory. Of course, the proof as stated also makes sense for an ordinary quantum system. So this is one way to prove relative entropy is non-negative in an ordinary quantum system. So that was the fact that Cassini used in proving the Bekenstein bound. And as dearly as I would love to explain monotonicity of relative entropy, which Aaron Wohl used in proving the generalized second law, I'm afraid that time just doesn't allow it. Thank you.
According to its form in quantum mechanics,
Yes.
it seems that the relative modular operator when you exponentiate it to an imaginary power,
Yes.
maps the algebra to itself.
Yes.
Does it remain true in quantum field theory?
Automatically, yes. A statement. It amounts to the fact that the limit of 0 is 0. So, mapping the algebra to itself is the same as saying, for a unitary operator to map A to itself means that if A is in A, then UA inverse commutes with B if B is in the commuting algebra. So the statement is that if in a cutoff theory this is true, then it remains true because the limit of 0 was 0. That might be a more concise way than, or a clearer way than I answered a similar question earlier. But all the statements that I made, which are supposed to remain true in limits, can be formulated similarly to this. And they're true because of statements like the fact that the limit of 0 is 0. Whereas if you want a sequence of operators to converge, you're on your own. You have to prove that. It might not be true. Any other questions? Okay.